and microcontroller, and currently we are studying the 8086 microprocessor. This is the 15th lecture in the complete series and 5th lecture for 8086 microprocessor. And today we are going to study the second part of simple programs in 8086. So what do I mean by simple programs is we are just trying to learn how to use this 8086 microprocessor together with its externally interfaced memory. And in that context, since this is 8086 microprocessor, it is a little bit different from 8085. So the highlight here will be that we will be putting more stress on the areas where 8085 is significantly different from 8086. So for today's case, one such area is while we make function calls and while we do assembly language programming. So up till now in the previous lecture, we have studied this code number 1 to code number 7, where we started from register data transfer. Then we started with addition of two numbers inside the registers and including the external memory. Then we saw the conditional and unconditional jump statements there. I mean, by using them, we made loops in this program, loops using jump statements. So you can make them by using conditional jump statements or even unconditional jump statements also. Then loops using dedicated commands where CX register was by default used as the counter register. So we also saw that this is something which is different from 8085. In 8085, there is no dedicated looping command. And in 8086, we have a dedicated looping command. And here, CX register acts as, by default, the counter register. So you don't need to decrement it always as your loop runs. It will be auto-decremented. And you can apply various condition checks on it to be able to come out of the loop or do something else. Right. Then we saw how stack is operated in 8086. Then we saw some indexing. Basically, indexing, it simply means that if you want to access a byte of data from the memory or a word of data from the memory, then what all ways are possible. So we have studied all these codes in the previous lecture. And in this video lecture, what we are going to do is we are going to study assembler directives, and we are going to see two modes, COM mode and executable mode of writing programs. So although when you write program in higher level languages like C programming language, whatever program you write is written for every kind of machine, right? So, but if you write programs in assembly, then you have to think of there are two ways of writing the same exact program. One is the .com mode and one is the .exe mode. So these both are applicable for disk operating system or DOS, it as it is called as now. So the DOS operating system or disk operating system, in that we can write programs in these two modes, COM modes and .exe mode, right? So they are different in the context that in COM mode, you only have one segment in which you write your entire program. So that one segment will be of 64 kilobytes, and there your data code as well as everything will reside. So it will make your program more or less like 8085, where you only had 164 kilobyte segment and you were writing everything in that, be it stack, be it code, or be it anything. However, for .exe mode programs, they are primarily meant for 8086 programming, and uh, when higher level languages, they if we try to convert these programs to higher level languages or higher level languages, if their programs are converted into this assembly language, this exe mode is highly compatible because here you can have four working segments concurrently, which are code segment, data segment, stack segment, and extra segment. And this mode is more suitable. But however, from the perspective of learning, we can do programming in both COM mode as well as exe mode. So exe mode is it will have little more syntax as compared to .com mode, but .exe mode is what should be frequently used. But we will be making programs in both of them. Then an important point is function calls. In 8085 function calls, we had various call statements, right? Like we had unconditional call statement, which was simply CALL, and there were conditional call statements like call on carry, call on parity, etc. But here in 8086, we only have a simple call statement, no conditional call statements, only a call statement is there, and no conditional call statements are there. However, we will see that call can be accomplished in various ways. One is called as near call and another is called as far call. Near call essentially means that you are uh, just transferring the control of your program into the same segment in which you are working. And far call, it simply means that you are transferring your control to some other segment, maybe. So this is a point of difference between near call and far call, and in the background they are executed in different ways. There are different things that will be put onto stack. So we will see all of those. So we will see this in exe style and in com style as well. So this is the topic of today. Briefly, I have given you what we are going to discuss. So let me just begin by showing you one slide where we will first begin with this discussion of how actually a program is executed in the actual hardware. So on the screen now, you see these are the levels of abstractions when you write some code. There is a high level language like C programming language could be there or Java could be there. Then there is the corresponding assembly code, right? Whenever we have written some code in C language or Java language or any other high level language for that matters, to be able to execute it on the actual hardware, it has to undergo some process. So first of all, we are going to discuss that process, what that process is. So a higher level language's code is first converted into assembly code, right? The language in which we are writing our codes is assembly code. So even if you write your program in higher level languages, it will be first converted to assembly language code, right? After that assembly language code is obtained, that assembly language from that assembly language code, we will make an object file, right? Object file which will contain the source code. Then, after making this object file, we will obtain its machine code, which will be usually a strings of ones and zeros or the language that machine understands. And that machine code will be simply run on the hardware. So let us first discuss how these processes happens and what all are the components which are responsible for converting this high level language into assembly code or assembly code into object file, etc. So first of all, when a higher level language code is converted to assembly code, we require a compiler, right? So this compiler is required to convert a high level language code to assembly language code. So that is why when you usually write your programs in C programming language, you have to first compile your code and then you will be able to run it, right? So when you compile your code, various files are generated inside your code folder. So you might have usually seen that .obj file is generated, then there is .exe file for your C code if it is correctly written. So all that comes from this process. So when you do compiling, your code will be converted into assembly code. After assembly code has been obtained, that assembly code by assembler will be converted to object file, which is .obj file, right? So .obj file is obtained. After your .obj file is obtained, it will be converted to executable file through the linker module, right? So linker will simply convert your object file to this machine code. And once machine code has been obtained, it can be easily run on the hardware. So these are the three important components which are involved in conversion of your higher level language code to this hardware code or the machine code. Right? Machine code can be easily run on hardware. Why am I telling you all this? I'm telling you all this because the .com mode and the .exe mode of the program writing style that we are going to discuss today, they will differ here. They will differ in their linking process. So when you write programs in .com mode, usually there will be some linking warnings or linker warnings because your data segment, code segment, etc. It all will be there in that one segment. So all the segments will overlap with each other. But .com style of mode is like this only. It will treat all the code, all the segments as overlapping segments. So there will be a linker error. Not error, it will be a warning. So you can neglect that warning and you can go ahead with your code if you know that your code is correctly written, right? So linker warning will be generated there. And it is also important to keep in mind that in higher level languages, you have file extension as xyz.c, right? So this xyz is the file name, it could be anything, and .c is the extension for C programming language. For any other higher level programming language, it could be different. For assembly language code, we have .asm because we are also currently writing the code in .asm format. Then they will be converted to .obj file, and finally in the machine code they will be in exe mode, right? So this is how the process of complete execution of your program from machine code to hardware happens. I mean, from higher level language to hardware happens. uh, so now let us try to discuss first of all how these .com and .exe modes, what are their specific things that we need to learn about them. So in the disk operating system or the DOS, which was a very initial operating system that we had. So we had two modes of writing program. One was called as .com style of writing programs, and second was .exe style of writing programs. Right. So uh, and once we decide which mode we want to write our code on, depending upon our requirement, it's not that you can write your code anywhere in that given segment, right? What happens is there is something called as program segment prefix, or abbreviated as PSP. This program segment prefix will consume 100 H locations, or equivalently 256 decimal locations. So this program segment prefix, it actually contains the operating system. I mean, once your microprocessor starts, what should it do? Where should the control be transferred to begin your program? What should happen in case when some error is encountered, etc. So that all thing is written in the first 100 hexadecimal locations, or 256 decimal locations. So first 256 locations, that is from 0 to 255, are consumed for writing that operating system, right? Or in hexadecimal, you can say that 100 H locations, so starting from 0 to 99 H, are busy. You cannot write any code into that, right? So this is your program segment prefix. So 100 H locations are usually used for that. And whether you write your program in .com style or .exe style, your data segment and extra segment registers will initially point to the PSP for every program run under MS-DOS. So if you are running your program under MS-DOS, then in that case, in whatever style you write your programs, be it .com or .exe, data segment and extra segment will initially point to the program segment prefix only, right? So this is the requirement. Now in .exe style, as we know that we can make uh, four segments, so you can just accordingly change the data segment and extra segments beginning address, right? Or the base address can be changed. But in .com program style, data segment, extra segment, stack segment, and code segment, all of them are the same. So you can't change them. You can, but then nobody will slash an error. But if you are writing your program in .com style, you have to take care of the fact that you never change the base address of DS, ES, SS, or CS into that, because this assembler will not flash any warning, right? It will it will not see it as an error, because logically, if you are changing the base address of a particular segment, it's allowed in 8086 programming. But if you want to write programs of .com style, you have to take care of the fact that you don't change the base address of any segment, right? So let us now discuss this .com style of programs in a little bit more detail. So .com style of programs is a one segment style of programming. I mean, all of the segment will be overlapping with each other, and your program will begin from org 100h. Org means origin of the program will be from 100h, for the obvious reasons that first 100 locations will be consumed first 100 locations will be consumed in the operating system part by the program segment prefix. So these 100 locations cannot be overwritten. So it is a pseudo-mnemonic. ORG 100H will simply mean that your program has to start from hundreds location. 0 to 99 in hexadecimal will be consumed by the operating system, and the stack pointer will point to the lowest even address. So FFFEH will be the starting of your stack pointer, and the stack will populate in a opposite direction to the increasing order of addresses. This is what we have already known. So these .com style of programs, they only consume 64 kilobyte, and they are loaded at org 100h. So one way of identifying the .com style program is there will be always this statement org 100h. So your program has to begin from 100h location, right? But this mode of programming does not make the full usage of 8086 capabilities, because there you are allowed to have separate four segments, but here you are working only in one segment, right? So there were languages like CP slash M, etc. For maintaining the compatibility, this .com style of programming came because earlier microprocessor, they did not have segmented memory. So these kind of programs were compatible to those microprocessors. Then .exe style of program, you will have four segments, right? Concurrently, you can have four segments: code segment, data segment, stack segment, and extra segment. They all can be made starting from different addresses, and you have to take care that they should not overlap. It is not necessary that every segment should be of 64 kilobyte, but the maximum allowable size for one particular segment is 64 kilobytes. So segments can be of 64 kilobytes each, but that is the maximum limit. You can have a segment which is smaller than that, and we are shortly going to see that in our program. It's not necessary that you will be always definitely allocated 64 kilobyte for one particular segment, right? So, and here the execution will begin from this location 000h. That is, instruction pointer will be initialized to 000h, right? So this style of program, .exe style of program, is usually suited for this Windows operating system. However, if you write usually .com styles of program, they will be suited to DOS or disk operating system more, right? So although this can also be done in your this DOS also, but then one characteristic of that is whenever the program will begin, you will see that the instruction pointer will be pointing to 000h. However, in this case, the instruction pointer will be pointing to 0100 in hexadecimal, right? So these are some differences between .com and .exe styles of program, and but when you program in higher level languages like C or Java, uh, you don't have to worry about whether you have to write program in .com style or .exe style. However, in assembly language, we have to worry about that. But in higher level languages, this all thing will be taken care of by the compiler. Compiler, it will do the conversions for you appropriately, right? So now let us begin by just seeing one very simple program. So let me start my EMU 8086. It is already in this um, trial mode version. So let me just open a very simple code for you. So the code will be, we are first of all trying to learn these assembler directives for .com style of programming, right? So we are now trying to code by using assembler directives, because assembler directives, they make your work a little more easy. So we are now using this assembly language programming with assembler directives, and assembler directives are different for 8086 as compared to 8085. They also depend upon the software you are using for emulation or the hardware kit. If it is a hardware kit, those assembly instructions will be provided by the vendor, but most of the instructions are common. There is no huge difference between the instruction set of assembly language, but some minor differences could be there depending upon the hardware that you are using or the emulator that you are using. So EMU 8086 has got its own assembly language. I mean, it has got its own assembler directive, so we will be using that. If you will program it in some other thing like Masum or Nasum. So these are also two other softwares on which you can do this 8086 programming. So there, these assembly directives will be very different, right? But they are simple to understand, and most of them are common. So here, the this program is for .com style programs using assembler directives, right? And the objective of the program is to add two numbers kept in memory by the name num1 and num2. We already know that in assembly language, through assembler directives, we can define these variables, num1 and num2. We have already done it 8085 and we are going to do it here also. And store the result in variables named result and carry. So we have these variables result and carry, and we are going to store the result of addition of num1 and num2 into that, right? So uh, the way this program starts is you have to write some segment. cseg is any name. It's not code segment only. cseg is any name. You can put any name here, and you have to give this keyword segment. I mean, you are going to start some segment from here. Its name is cseg. And when the segment ends, the corresponding statement will be cseg ends. So if you want to write any segment, we do not know which segment it is, whether it is code segment or data segment or stack segment or extra segment. We do not know what segment will it be. But if you want to write any segment, you have to give this syntax. Some name should be given and then this segment keyword. And when the code ends, you have to write that particular name and ends. So that segment will end. Now, inside this segment, you will be writing your assembly language code, which will be a combination of assembler directives plus the regular instruction sets of 8086. Now, here we have written this keyword assume. Assume DS. DS is a register which is inside your microprocessor, which we have seen. It holds the base address of the data segment. Similarly, you have got this data segment is there. Let us also call it this data segment. Let's me put ES also here. I have missed it. So let me just save this code. So you have got this data segment, extra segment, stack segment, and code segment will automatically be there. And you have initialized them with this cseg. Cseg was the name of the segment you have started. So in .com style of programming, it is mandatory, right? It is mandatory because your data segment, extra segment, and stack segment, they should have the same base address. So the base address of cseg segment will be kept here. And this is mandatory in .com style of programming as we have just discussed, right? So code segment will automatically be initialized by the cseg because code segment, when you use an emulator, the code segment is prefixed when you try to run any program. So data segment, extra segment, and stack segment will automatically be also initialized by this particular segment. And when you write your program, you have to write this start keyword. So from here, your execution will begin, right? Before that, you have given org100h, and this is for obvious reasons because you know that 100 locations will be consumed in writing the operating system. So org100h will be there. And then when you want to execute your program, you have to write the start label, right? So this is a label that you have to write, and you have to end this label after this program finishes. So you have written your simple program here. This simple program is written here, and the only important point to note here is that what you are doing is you are initializing all the segments to the same segment. Means data segment, extra segment, stack segments, etc. are all initialized to the same segment. Now one might ask the question, how is code segment by default it will be initialized to the C seg only? So the code segment will by default be initialized to C segment because it contains this keyword org100h. So wherever this org100h is there, that segment, because we have made this segment, it will automatically become the code segment, right? So code segment is automatically this segment, whether the name is cseg or not, whether the name is something else, it hardly matters. But since it contains org100h, so this segment will automatically become the code segment. And inside the code segment, you have assumed that all the other segments are also pointing to this particular location. Now the usual program begins in AL. You have taken num1. Now where does this num1 comes from? Let me discuss that first. So you can see at the bottom of this code, you have defined some variables, right? So num1 db means defined byte. It will be of 1 byte. Num1 is a variable name. db means defined byte. So it will be of size 1 byte and its value is 15 in hexadecimal. Right. Similarly, num2 has been defined as a byte and its value will be f1h. Zero is appended for the obvious reasons, because if your number starts from A B C D E F, then it has to have a zero before it. So it will make it a number. So F1 will be the value of num2. Result is also defined by it, but we do not know its value. That's why we have put a question mark. So it will contain some garbage value. And carry, it will also be of 1 byte and it will be a question mark here. So now what you have done is in AL you have moved num1. So whatever is num1, that is 15h, will be moved to AL. Then add AL comma num2. So num2 will be added to AL and the result will be by default stored in AL register by this add command. Then you have moved into the result variable the value which is kept in AL. That means you have moved the result of addition into AL register. But suppose if there is carry, what arrangements will you make? So the logic for carry that I have applied here is you simply just rotate your accumulator register by left side. So when you will rotate it by left, what will happen is that if some carry is generated, it will automatically come into the least significant bit, right? So first of all, what you have done is rotate AL by only 1 bit. So by 1 bit, your this AL register will be moved, and because of that process, because since you are moving it in the left direction, so that carry will automatically come to the least significant bit. So this is similar to what we had in 8085. We will discuss this instruction in great details later also when we will discuss the complete instruction set. So this will be moved by 1 bit. Now what you will do is you will AND the contents of AL register with 000001B. Why? Because you're only interested in the last bit. So the binary number, this 7 times 0 and 1, and when you will add it with that AL register, you will simply get that last bit. And you will simply move that into the carry variable. So move carry comma AL. So after ending, you will be only left with carry. If carry is occurring, this value will be equal to 1, and if the carry is not there, it will be simply equal to 0. And then this move AX4C00H and interrupt 21H is this. We will discuss what interrupts are later, but this is just to end your program. Right? For now, you can understand that this is just to end your program. Interrupt 21H has been called, and your program execution will be ended there. Right? So here you can see that in this particular program, you have defined the data here, and the rest of the portion is your code portion, which you have defined in the same segment, which is called as C seg, right? So in this way, your .com style of programming is done. I mean, this is one simple segment inside which you have defined your data, inside which you have defined your code. If you require some stack, then you can also work on that particular thing, right? So let us just execute this program and let's see what are the things that are important to note there. So this is a .com style program. So you can see that instruction pointer will begin from 0100. The address of this code segment is by default taken as anything by this assembler, and the same address for extra segment is given. For data segment, the address is same, and for your stack segment, the address is also same. So the important point to note here is instruction pointer is 0100, right? And it is for the user to make sure that the base addresses of these DS, ES, and then SS and CS are not changed when we run the .com style program. So let us run this program simply and see if the addition happens or not. So you can see that first of all, let us check whether these variables are stored in your actual memory or not. Num1, num2, db, 15, f1h. So they are at the end of your program, right? And your program has started from 0700 is the base location. And when we started the program, it was from 0100. So let me put 0100 here so you can see where the program is written from. So yes, these are the locations. So when your program will end, So we will see when the zero zeros or some constant values start to appear. So this 1919 is the default value that has been stored there. So before that your program has ended, right? So the last four bytes of your program will be the data byte, 1, 2, 3, and 4, I guess, right? So here you can see that 15 is here, 0f is here. Yeah, so 15 is here, so 0f1, which means f1 is here, and the next two locations are vacant. So they are kept for result and carry. So they are already there. For result and carry, they are already there. And they have been initialized as 00. Otherwise, they could also be some garbage values because we had put a question mark there. And these four locations are result for num1, num2, then your result and carry, right? So that has been there. So the only important point to note here is data is also here, and the code portion is also there. The mnemonics for the code is also there, and this instruction pointer was initially started from 0.00. So after the execution of this code, the result should be stored here. So let me just run it. So this has been run completely, and the messages program has returned the control to the operating system. So it comes because of this interrupt 21H only, right? So let us see whether the results are there or not. So the code segment, its beginning was 0710, and here we have 0000. Right. So let us now see at the end locations, have we got the result? Yeah. So here we have 15 stored and F1 stored. When we will sum up 15 and F1 in hexadecimal, the result will be 5 plus 1 is 6, which is correct, and F plus 1 will be 1 0. So 0 is stored here, and inside the position of carry, you have got a 0 1. So this is the correct result, 0 6 and 0 1. So in these two locations, your result has been stored. Right. And so this is the way your .com style program has run. Now let's have a look at .exe style of programming. So let me just open that corresponding program for us. So this is .exe style of program. In this .exe style of program, again the objective of the program is to add two numbers kept in memory by the name num1 and num2 and store the result in result variable and carry, right? So this is the aim of the program. This is the same program essentially, but the mode of writing is now .exe style. So in this .exe style, you can see that now the data segment is separate. Now the code segment is also separate, right? So you don't have to put your data essentially into the code segment. You can now define segments of different sizes, right? So here you can see that num1, num2, result and carry have been defined in the data segments, and the only thing that you need to define a segment is just give it any name. It's not necessary to give it a name of data. This data could be anything. You can give it your name. So data segment and data ends. So how will the program know that this is the data segment? So the thing is simple. When you will write your code segment, inside your code segment, you have to write this assume statement where CS register has to be initialized with code, so it is already initialized with code, and DS register has to be initialized with data. So this data segment will be taken up here. Even if you write your name here, this code will work fine. So DS, whatever base address you will put here, it will be triggered as your data segment. And here you can note one point of difference that this CS has also been initialized because here we do not have a statement like org100h. That statement was present in .com style of programming, but in this style of programming we do not have that. That is why we have to manually initialize this code segment also. So that has been initialized. Then the regular program is there. We have to start it, and everything will be done here in the same way. This is the same exact program, and then you can simply execute it. So let us see what happens on emulation. So emulation, the first thing that happens is you can see that instruction pointer now begins from 0000h. So in the earlier case, the code segment was beginning from 0710h, but here it is beginning from 0711h. Now, why has it happened? Because the initial first 256 locations that were reserved for your PSP they were inside that com style of program only in the code segment of that. But here the code segment will begin just after that. And that is why this instruction pointer it starts from 0000. Earlier it was starting from 0100. Right? So the code segment has begun from this section. Data segment, extra segment also have begun from that section. But as soon as we will execute this program, so the data segment etc. will be initialized appropriately by these commands move ax comma data and ds comma ax etc. So they will be appropriately initialized and the things will happen there. Right. So let us see that now you have changed your data segment address 0710. Here it is 0711 and data segment's beginning address has been changed. So and in the same way the program will be executed. So if you want to check the data segment after the execution of this program, I mean interrupt 21H will be called later. So let us check it by putting 0710 there. So this is 0710 and let us start it from 000H. So you can see that 15 and F1 is here and after addition 06 and 01 have been put there. Rest all locations are 0, right? So this data segment, it has certain default bit that will be there, default size that will be there if you declare it. It will not be 64 kilobyte to begin with. It might be some less also, something less also, but there will be some default small weight. But theoretically, if you want to define a 64 kilobyte data here, that is possible. So you can define various arrays inside this if you require that location. Various uninitialized arrays can be defined, and we will see how to define those arrays in the coming programs. Right. So this is your .exe style of programming. The only important thing to note here is that IP will start from 0000 to begin with, and data segment's base address can be changed. It can be changed as compared to the code segment, right? So this is how .exe and .com style of programs are written, but we can follow one style. If you really want to use the full capabilities of 8086, you have to follow the .exe style, or otherwise you can write your programs in .com style also if you just want to learn, because in .com style programming is a little easier, right? So now let us move on to this function calls, right? Function calls, and there are two very important points to understand. One is near call, as you can see here, and another is far call. So we will only see these two near and far call in .exe style of programs, and then we will also see this .com style of programming, right? So EXE style of programming, because EXE style of programming will help you understand everything from the perspective of 8086. Otherwise, .com style of programming, it will be as good as 8085 programming. So let me begin by showing you this program. We are going to make a near function call in .exe style, right? So let us begin this program. Obviously, data segment will be separately defined here. So we have defined the data segment, but it does not contain any data because we do not want to keep data in this programming data segment, right? And near call, what it means is you are essentially jumping within the current segment that you are using. So that's what we mean by a near call, right? So you have defined the code segment here. You have assumed that CS is code segment, DS is data segment, and then you have started your program. So since we are studying function calls, so we will define one main function. So this is main. Proc means procedure. Function's alternative name is procedure. So in assembly language, we call it as a procedure. So this is the main function, main proc, and here you have simply just initialized your data segment first, and after initializing your data segment, you have kept some data in BL and CL register, which is 01 and 02H, and then you have called an addition function, which will simply add the value of these two things, and the program will be over. So it's just a simple program of addition of two numbers. And here your main procedure has ended. So main and P. So the function that you have written is within the same segment. So before this statement code ends, you have written a function addition underscore function proc, means addition underscore function procedure is defined here. So whatever you see in blue is the keyword. And here you are simply adding BL and CL and simply returning. And this addition function and P means end procedure. So this is the way how functions are defined in assembler directives says, right? And you can see that you have defined the function within the same segment. So this is the beginning of your code segment, and here code ends. So inside this only you have defined your function, right? So that's what we have done here. And when you will run this, what will happen is whenever a near function call is made, that means whenever you want to call a function which is written within the same segment, in that case, we already know that whenever from a program we jump to the location of that function, you have to put in 8085. In 8085, the contents of your program counter, your program counter's content will be put onto that particular stack. So here, what we will do is we do not have a program counter. We have a combination of two registers, which is CS and IP. So the code segment's base address and its instruction pointer, because the combination of this will do the same job of that program counter used to do in 8085. So here we have CS and IP. But the important point to note is when you are making a intra-segment jump, means within the segment jump. So within the segment jump, only the contents of instruction pointer will be put onto the stack, not the contents of CS and IP. I mean, both of the contents CS and IP will not be put onto the stack if you are making a within the segment jump. Only the contents of instruction pointer will be put onto the stack. So let us verify this fact. Since this is a .exe program, so segments are different and your instruction pointer will be by default initialized with 0000. So you can see that instruction pointer is initialized with 0000 and your code segment's base address is 0710, right? So uh, let me just first check what is the content of stack as of now, right? Because the stack is responsible for containing your program counters, sorry, not in program counters in this case, it will be containing the combination of either CS IP register or only IP register, right? So in the case of near call, it will only contain the contents of IP registers. Let me just execute this program up till this point, call addition function, and then let's see what should be the contents. So now this yellow line makes it very clear that this is the next instruction to be executed. And if it is a near call instruction, definitely this will take 1 byte, and this addition underscore function is the address. So it will consume 2 bytes here, right? So it will consume 2 bytes here. So this will be complete 3 byte instruction. So you can see here that the code segment's content will remain fixed 0710 and the instruction pointer is 0009. So 0009 location will contain the hexadecimal equivalent of call 0009 plus 1. That means 000A and 000B will contain the 2 bytes of this addition function label, right? And the 000C location will be the location of halt statement. So before we make a jump to this particular location, this 000C, which will be the content of instruction pointer if this program were to be executed in sequence, so that content will be put onto the stack. And what is the beginning of this stack? So you can see that this stack segment, it also begins from 0710. So 0710 is already there. So let me just put FFFF here, which is the bottommost location, and let's check at those locations. So this is the 0710 FFFF location. If you will add that, you will get this result. So 4 locations before that, there is nothing, absolutely nothing. All of them are zeros. But let me execute this. So 000C should be stored here. So let me run it a single step. So now the function has moved on to this, the control has moved on to this particular addition function. And now let us check on the status of our stack. What is there on stack? So let me just go to this. Okay. So you can see that there is this 000C there, right? So only the contents of instruction pointer have been put onto the stack 00 and 0C. 00 is the higher order byte, so it has been kept at FF location, and 0C is the lower order byte, so it has been kept at FE location. So only that content has been put here. The content of CS, which was 0710, is not put here. So this is one very important point to note about near call. Whenever you are making a near call, only the contents of IP register will be put onto that particular stack. And near call simply means you are having all your functions or sub functions which are defined in the same segment, which happens to be code segment for our case as of now. Now, next call could be a far call. So let me just open a program of far call in .exe style. So this is far call in .exe style. So here you can see that in this extra segment, I have defined this function. In this extra segment, I have defined my addition function, and it is the same program, essentially the same program that we had earlier. So the function, the only point of difference is the function has been defined in some other segment, right? Now, code segment has been defined here as usual, and this is the usual code that you have, which is the main procedure. So this main procedure is now defined in your code segment, and in the extra segment I have defined my function. So here assume CSS code segment, DSS data segment, and ESS extra segment. Now, starting of the program. So if you are programming it in EMU 8086, you need to mandatorily write these four statements if you want to make a far call, right? So this constraint will not be there in MASM programming or NASM programming if you are using those emulators or assemblers. But every emulator has got its own style of assembler directives in programming. So for EMU 8086, these four lines are mandatory. So you have defined offset print me and segment print me. So this is the offset address, and this is the segment address. Both will be of 16 bits. So you have given them a memory location of define word, and they are initialized with garbage value. So these are the two values which initially will contain no nothing, and then through these two statements, offset print me and segment print me, you will move a value of addition function. So this addition function's value, this addition function's base address will be kept in this offset print me. So this will contain the offset address, and in this segment print me, it will contain the segment address of addition function. So segment's address of addition function will be calculated by the seg command. So wherever this addition function appears, that particular segment's base address will be kept in segment print me variable, and offset of that function will be kept in addition, because it might be that before this function you have also defined something, some data, etc. So the offset of this particular addition function will be kept in offset print me variable, and segment print me variable will contain the address of the segment in which that function has been defined. So it is mandatory to write these four lines if you want to make a far call. And then the rest of the program is usual. Whenever you will call this program, there is this function called as far addition. So the difference in syntax for calling a far function is call. You won't simply write addition function. You will write call far addition function. So if you will mention this far, these four locations will be used for calculation of its offset address as well as the base address. And then this appropriate function will be called. Now, when we will emulate this program, the only important point to note here will be that in the case of far call, the complete address of the next instruction to be executed, that is the code segment, that is CS register, as well as the instruction pointer, will be put onto the stack, right? So let us see that fact, and that is more important. So let me just run this code. Since this is a .exe style program, so IP has beginning from 0000, and the code segment is 0711. Its beginning is this. So let me run the program up to the point where we have called the function. So let us see. Yeah. So here I haven't called the function. This yellow line means this is the next instruction to be executed, right? So let us check first of all the stack value. Or let us first discuss what is the address of this halt instruction. Now, this call function for far variable, it will have the contents of CS and IP will definitely be put onto the stack. But let us discuss what will be the size of this call instruction. So call will consume one byte, and this address that you have got for addition function, it will be two words. Two words, that means you will consume definitely two words means 4 bytes will be consumed there, right? So as of now, the address of code segment is 0711, and the address of instruction pointer is 0019. So definitely, after one nine, you will have 20, right? After 19, you will have 20. Then there will be four such locations which will be consumed by this particular address function. So those values should be stored there. So remember the value of code segment, which is 0711, and IP is 0019. So the location of halt will be after calculating the complete size of this particular thing and then halt instruction. So let me just first of all check the content of stack. So stack segment, you see the address is 0710. So let me put 0710 here, 0710, and let me put FFFF here because we want to see the last location of that. So as of now, this instruction has not been executed, and if you go up, you can see that the complete stack is empty, right? Now, if you execute it by a single step, then the function has moved the control to this particular extra segment, which is very obvious because function will do that. But now let us see the contents of your stack now. So here you can see that now stack has been filled with some content, and let us see what it is. So the contents of code segment and IP will be put onto that. So the contents of this code segment was definitely 0711 to begin with. The address was 0711 to begin with. Now it has been changed because it has been moved to extra segment. But when we began, it was 0711. So it is already there, and 001D. 001D will be the address of the IP register. Sorry, 001D will be the address of the halt instruction that we have seen here. Why? Because this call will consume 1 byte and 4 additional bytes will be consumed by this addition function. So call will be placed at some location plus 4 additional bytes, means 5 additional bytes will be there, and then your uh, IP will be calculated for halt. So if we step back, we can again just calculate that. So I'm again moving to an instruction where we haven't called this, and you can see the contents of CS. It is 0711. We haven't called the call function yet, and the address of CS register is 0711, and here we have IP, which is 0019, right? So into this 19, the next location will be like 20, right? Because you know, in hexadecimal numbering system, you will have that. Then after that, you will have A, B, C, D. Those four locations will be consumed by this addition function. So 0019 will be here, and then 20, then A, B, and C will be consumed by this addition function because that will be complete CSIP location of that. So now if you step again, then you have called here. Then let me just move on to the last portion of the stack. And that's what you can see here. If I move upwards, so 0711 is already there and 071D is already there. So that is how this CS and IP has been kept here. So that is another point. Address calculation is another point. But the main point to note here is that the content of CS and IP, both registers have been kept. So in far call, you have to keep the content of both of that on this register. So definitely every instruction, every call instruction, if it is a far or near instruction, depending on that, it will consume different bytes in the memory, it will be executed in different way. But however, in 8085, it was completely the same. If it is a call instruction, it's a call instruction, and it will be putting the content of program counter onto the stack. But here, the difference will be that sometimes you will be putting the content of only IP register, in which case it will be a near call, or otherwise, if it is a far call, you will be putting the content of CS as well as IP, both of the registers, right? So this is how we write a function call when it is a far call, and it is written in .exe style. So I will put it here .exe style and save it also. Now quickly let us also see if we want to write it, if we want to write a function call using assembler directives in .com style. So this is in .com style. Yeah. So in the .com style, you can easily see that you have this org 100x statement. Then inside the code segment only you have defined the main procedure. You have ended it, and after that you have defined this addition program. So now everything will happen inside code segment only because that is the characteristic of .com style of programming. So this is how easy it is to do it in .com style. So from a learning perspective, you can use .com style also, but you should also keep in mind that .exe style is also there in which the programs are written. So let us just emulate this and see this. Since it is in .com style, so definitely you cannot be making inter-segment jumps. Only intra-segment, that is within segment jumps will be possible. So definitely your IP has started from 0100, and if you just check your stack, which also happens to be initialized from 0700, and FFFF is the last location. However, the stack pointer will be at FFFE. So you can see that it is completely vacant as of now. But when you just execute this, I mean, now this call my addition instruction. If you see this, this is consuming these three. This will be consuming 3 bytes here, and you can see that 0700 is this correct address, and 0104 is there. So 0104, 5, and 6 locations will be consumed by this call instruction, and seventh will be move CX. So this seventh one, that is 0107, will be kept onto the stack. So let me execute this, and let us now check the base of the stack. So FFFF, and let us now check this. Yeah. So you can say that 0107, higher order byte 01 and the lower order byte 07 of this instruction pointer is already there. However, for code segment, we do not have anything because in COM style of modeling, we can only move within the segment. We cannot go outside the segment. So every time the call that we make is a near call only. No far call there will be allowed. Like, so this is how you can program that in COM style of modeling. So in current lecture, what we have essentially done is we haven't learned anything new, but from the perspective of 8086, there are some points which were different in 8086 as compared to 8085. Okay, how many of you are still here? Please raise your hands.